Hello everyone, and welcome back to the How Machines Work series. In our previous lesson, we learned about force, motion, and Newton's laws. We discovered how forces cause objects to move and how engineers use physics to understand machine behavior. Today, we're going to focus on a special type of motion that appears in almost every machine: rotation. Learn why machine parts rotate, what torque is, and how engineers use rotational motion to transfer energy and perform useful work. Before we begin, let's quickly review what we've covered so far. We learned about force, motion, Newton's laws, and the different forces that act on machines. Now we're taking the next step by answering an important engineering question: why do machine parts rotate instead of moving in a straight line? The answer involves a concept called torque, which is one of the most important ideas in mechanical engineering. By the end of this lesson, you'll understand how torque creates rotational motion and why it is essential in machines. Let's start with rotation itself. Rotation is motion around a fixed point or axis. Unlike linear motion, where an object travels in a straight line, rotational motion causes every point on an object to move in a circular path around the axis. We see rotation everywhere. A bicycle wheel rotates around its axle to move the bicycle forward. Fan blades rotate to create airflow. An engine crankshaft rotates to transfer power. Wind turbines rotate to generate electricity. Engineers often prefer rotational motion because it is efficient and can continuously transfer power through mechanical systems. Now let's introduce torque. Torque is the turning effect produced when a force acts at some distance from a pivot or axis. In simple terms, torque is what causes rotation. It's helpful to compare force and torque. Force creates straight line acceleration. Torque, on the other hand, creates rotational acceleration. The stronger the torque, the easier it is to make an object rotate. Engineers measure torque using a unit called the Newton meter, or Nm. Even if you have never heard the word torque before, you've experienced it in many times. Think about opening a door. If you push near the hinge, it is difficult to open. If you push at the handle, it is much easier. The reason is that the handle is farther from the pivot point. The same principle applies when tightening a bolt. A longer range allows you to create more torque with the same amount of force. When you turn a steering wheel, you're also applying torque to control the direction of a vehicle. These examples show that the distance from the pivot plays a major role in rotational motion. Three main factors affect torque. The first is the magnitude of force. The greater force produces greater torque. The second factor is the distance from the pivot point. Increasing the distance increases torque, which is why long handles and long wrenches are so effective. The third factor is the direction of force. Only the part of the force that acts perpendicular to the lever arm contributes fully to torque. Engineers use all three of these factors when designing tools and machines to maximize efficiency and mechanical advantage. To calculate torque, engineers use a simple equation. In this equation, tau represents torque, F represents the applied force, and R represents the perpendicular distance from the pivot point. This formula shows why longer tools are more often effective. If the force stays the same but the distance increases, the torque increases as well. This is why mechanics often use longer breaker bars to loosen tight bolts that would be difficult to remove with a short wrench. Torque is not just important in hand tools, it plays a critical role in machines. Car engines produce torque at the crankshaft, which is transferred through the drivetrain to the wheels. Power tools use electric motors to generate torque that spins drill bits and saw blades. Wind turbines use torque produced by the wind acting on the blades to turn generators and produce electricity. In all of these examples, torque acts as the link between applied forces and useful rotational work. Let's look at real engineering example. When a cyclist pushes down on the pedal, a force is applied. The force creates torque at the crank arm. The crank rotates and transfers power through the chain. The chain drives the rear sprocket, causing the wheel to rotate. As the wheel rotates, the bicycle moves forward. This process demonstrates how force is converted into torque and then used into useful motion. Without torque at the crank, the bicycle's drivetrain would not be able to turn the wheel. So, let's review what we learned today. We defined rotation as motion around a fixed axis. We learned that torque is the turning effect of a force and explored the factors that affect it, including force, distance, and direction. We introduced the torque equation and saw how engineers use it to analyze and design machines. Finally, we looked at real-world examples showing how torque appears in tools, engines, turbines, and bicycles. In the next lesson, we'll connect everything learned so far by exploring work, energy, and power. We'll answer an important question: how much work does a machine actually perform? Thank you for watching, and I'll see you in lesson 5.